Hello, hello, and welcome to this video. In this video, we will finish the documentation of Hashmap and then we will move on to hash set. So we had covered till drain and we will resume from here. So if you have not watched the previous video, then please go and watch the previous video. As such, you should watch the entire playlist in order. But in any case, we resume here and let's get started. So drain clears the map, returning all key value pairs as an iterator keeps the allocated memory for reuse. If the return iterator is stopped before being fully consumed, it drops the remaining key value pairs. The return iterator keeps immutable borrow on the map to optimize its implementation. So we have created this hash map here and we call drain and we take one. So if we take one, then key can be either one or two, and value could be either A or B depending on the key. And after that, the iterator would be dropped and our hash map would be empty. Then we have extractive. So it takes a closure here to drop it. Creates an iterator which uses a closure to determine if an element key value pair should be removed. If the closure returns true, the element is removed from the map and yielded. If the closure returns false or panics, the element remains in the map and will not be yielded. The iterator also lets you mutate the value of each element in the closure regardless of whether you choose to keep or remove it. If the returned extractive is not exhausted, example because it is dropped without iterating or the iterator or the iteration short circuits, then the remaining elements will be retained. Use retain with a negative predicate if you do not need the return iterator. So, for example, we are going to split a map into even and odd keys. So what we first do is we iterate our 0 to 8, that is 0 to 7 will be included, and we collect it, okay, and create a map out of it. So key value will be both same. And then we extract if the key is divisible by 2 and we collect it into another Hashmap extracted. Now events is you iterate over extracted dot keys and then we copy and collect into vector. So that would be your events. And then the remaining will be of course odd. Okay. So you sort them and you find them 0 to 4, 6 and 1, 3, 5, 7. Then we have retain, which also takes a closure, retains only the elements specified in the predicate. In other words, remove all key value pairs, all pairs key value for which the closure returns false. The elements are widgeted in unsorted and unspecified order. So again, here we create a map of 0 to 7 and we retain if they are even. So the length will be eventually 4. Performance-wise, in the current implementation, the operation takes O capacity time instead of O length because it internally visits empty buckets too. Then we have clears the map, removing all key value pairs, keeps the allocated memory for reuse. So if you call clear, it will become empty. Next is hasher, return a reference to the map's build hasher. So we have a hasher from random state new and we create a hash map with hasher. And if we call hasher on the map, then we will get the random state. Then we have hash map with KVSA where K should satisfy the trait of equality and hash S is build hasher and A is allocator. So it is the implementation of that and we have now reserve which takes an additional argument of usize, reserves capacity for at least additional more elements to be inserted in the hash map. The collection may reserve more space to speculatively avoid frequent pre-allocations. After calling reserve, capacity will be greater than or equal to self.length plus additional. Does nothing if capacity is already sufficient. Panics if the new allocation size overflows view size. So we have a hash map here of string and I32 and we can call reserve on it. Then we have try reserve which returns a result enum with success or try reserve error. Tries to reserve capacity for at least additional. It's the same thing, same description here. The error is if the capacity overflows or allocator reports a failure, then an error is returned. So try reserve seems to be better than reserve, so use as you want. Then we have shrink to fit. Shrinks the capacity of the map as much as possible. It will drop down as much as possible while maintaining the internal rules and possibly leaving some space in accordance with the resize policy. So suppose we reserve a hash map with capacity 100, we insert two elements, then at this moment capacity would be greater than 100, and if you call shrink to fit, then the capacity will be at least 2. Then we have shrink to, which takes an argument min capacity, shrinks the capacity of the map to the lower limit. It will drop down no lower than the supplied limit while maintaining the internal rules and possibly leaving some space in accordance with the resize policy. If the current capacity is less than the lower limit, this is a no-op. So we create a hash map with capacity 100, we drop two elements, capacity would be greater than 100. And then we call to shrink to 10, then capacity would be greater than equal to 10. And if you call shrink to less than, then it's a no-op, and capacity would be at least greater than 2. Because here current capacity is less than the lower limit. Okay, current capacity is not less than lower limit here. Current capacity is 2, so it's not a no-op. Looks like a no-op here. If the current capacity is less than lower limit, no, it won't be a no-op. Current capacity is not lower than the lower limit here. Then we have entry, gets the given keys corresponding entry in the map for in-place manipulation. So suppose we have a letters map, and for character in a short, retired, and funny, we take the characters out of it, and we call entry on every character and modify it by replacing the counter by 1 or insert 1. So here initially it will, for example, it will see A, it will insert with count 1, and then on second day counter will be increased. So A will have a count of 2. Similarly, if you look at S, then it will have count 1 here and then count 2 here. So counts are taken like that. T will have count 3, so it will have count 1 here, 2 and 3. So accordingly, all the things will have count, and you can see that Y will have count none. Then we have get function, which we just used here. Okay. It returns an option enum, returns a reference to the value corresponding to a key. The key may be any borrowed form of the map's key type, but hash and EQ on the borrowed form must match those for the key type. So we insert an element, we get 1, we get some A, and if we try to get 2, we won't find it. Then we have get key value, so it returns key value. The key here must satisfy borrow, and Q must satisfy hash plus EQ plus side. Side meaning its side should be known at compile time. Returns the key value pair corresponding to the supplied key. This is potentially useful for the key types where non-identical keys can be considered equal. For getting the ampersand k stored key value from a borrowed ampersand q lookup key, or for getting the reference to a key with the same lifetime as the collection. The supplied key may be any borrowed form of the map's key type, but hash and EQ on the borrowed form must match those of the key type. So suppose we have here a struct S of ID 32 and name a static string derives from clone, copy, and debug, and we define partial equality for S. So self.id should be the .id. And we have empty implementation for EQ, and we have hash for S. So we hash the ID with the state. So state will depend on what we are going to hash. Okay. Now it is the state hash which we are trying to implement here. Now we let j underscore a is equal to s id1 Jessica, then jb is id1 named Jess, P is equal to S, ID 2, name Paul. Now we can assert that J is equal to JB because J is equal to JB. IDs are same. Now we create a new hash map. We insert J and the value is Paris. And if we get the key value of J, we will get J and Paris in an option NM. If we try to get JB, we will get J and Paris here. Okay. So this J and Paris. So J and Paris. So J is basically this ID1 and JB also has ID1 and we have inserted J with Paris. So if you try to get JB is ID same, but the value would be Paris. And if you try to get the key value and %P, that is ID2, we will get none. Then we have get disjoint mutable, which takes a case which satisfies the trait Q and N. So N is not satisfied. It's an array of type Q and length N, and N is of U size. Now it must satisfy the K trait here, which is borrow Q, and Q should satisfy the trait hash EQ and side. Attempts to get mutable references to N values in the map at once. Returns an array of length N with the results of each query. For soundness, at most one mutable reference will be returned to any value. None will be used if the key is missing. This method performs a check to ensure there are no duplicate keys, which currently has a time complexity of order n square. So be careful when passing many keys. Panics if any keys are overlapping. So we have a libraries map here. We insert Baudelaire library with 1602. I cannot read this. Athenium to 1807. Herzogen Anna Amalia Bibliothek to 1691. Library of Congress to 1800. And then we try to get the Athenium and Bodleian library, and it will be Potens Same someday. Similarly, if we get Athenium and Library of Congress, we will get the 1807 and 1800. And if you give a missing key, for example, New York Public Library, you will get none here. Now, okay, this example panics here. So if the keys overlap, then it will panic, okay, because we can't get two mutable references here. Remember that the value is mutable, and if it is the same key, you are basically asking for two different mutable references, which it will refuse to give. Over here, okay. Then we have got disjoint unchecked mutable, dangerous function because it is unchecked. So the description is same. For a safe alternative, we have this. Following this method with overlapping keys is undefined behavior, even if the resulting references are not used. So use it with the care. Okay. Then we have contains key. So we pass in a key of type Q, and K should satisfy the borrow trait, and Q should satisfy hash EQ and size. Returns true if the map contains the value for the specified key. The key may be any borrowed form of the map's key type, but hash and EQ on the borrowed form must match those for the key type. So we have a hash map with the key 1 and value 1, and does it contain key 1? That is true. It returns a boolean, okay? So contains key 2 will give us false. Then we have get mutable, which will give us a mutable reference to the value corresponding to the key. Description is same, so it will be an option num, and if it is mutable, so we can modify it. Then we have insert. So it takes a key and value and return an option num with type V. Inserts a key value pair into map. If the map did not have the key present, none is returned. If the map did have the key present, the value is updated and the old value is returned. The key is not updated though. This matters for type that can be equal to without being identical. See the modular level documentation for more. So I don't think we will ever go there, but in any case, we insert 37 comma A, none, and then the is empty will return false. Okay. And then we insert 37 comma B and insert 37 comma C. And at this moment, it will return some B and the 37 will have value C. This is nightly API, we don't care, and we have removed. Okay. So similar description, you can read this. Removes a key from the map, returning the value at the key if the key was previously in the map. The key may be borrowed, it's the same description. So we have a hash map new, and we have 1 and A, and if we say remove 1, then it will give us the value some A. And if we try to remove again, we'll get none. Then we have return entry. Similar description, removes a key from the map, returning the stored key and value if the key was previously in the map. And the remaining description is same. So we have hash map new, insert 1 and A, and we remove entry 1, then we'll get 1 and A. And if we try to remove again, we'll get none. After this, we have trait implementation. So for trait implementation, we have studied several traits in traits video. You should watch that. And it is similarly, it is actually not possible to go through all the traits because that will make the videos too long. So we now know how to use Hashmap. And with this, I will end this video here. In the next video, we will look at hashed documentation. And after that, we will look at iterator. So when I say iterator, what I mean by that is, let me show you. Iterator. Let me pull the all.html. Okay. So here we want iterator. So we are talking about this file. So after hashed, we will go through this and we will look at all the methods of the iterator module, because that is going to be fundamental to what we are going to do next, that is functional programming. Once we are done with functional programming, we will approach multi-threading. So the order is that we will finish hash set, then iterator, and then functional programming, then multi-thread programming. So with this, I'll stop here, and I hope that you have enjoyed this video and we have learned something useful. So thanks a lot for watching the video, and we'll meet again after 4 days. That is, if I can. And thanks a lot for watching the video again. So till then, till the new video, stay curious, keep learning, and most importantly, enjoy.